Together. Organic.
Oh, yeah, it doesn't matter. What the other thing else?
Something. Okay. Okay. Fine. You want me to share it to your? I need to have more on it. I like it. Yeah. Okay.
Good. Got a friend that's visiting from Singapore, so we took her to downtown visit. That's the thing to take people to in California without actually paying to go into the park. Exactly, but they have the Disney store there, so it's nice. She has a 4-month-old baby, so the fact the baby made the plane ride from Singapore to LA is pretty crazy. So very cute, very well behaved.
That's great, that's good.
How are you guys? Oh, nice.
I saw.
Oh, yeah. Yeah,
Weird, all the billboards, seeing them all,
yeah,
like.
it's its own bubble.
It's so weird. People, visions. That. And the San Francisco and the. So.
Oh,
It's a dazzling.
nice, nice. That's rare.
Yeah.
Okay, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good to hear. All right, so today we're still talking about element types, and so from last Tuesday, because last Thursday we had our activity. Last Tuesday we talked about the 2D elements, and so we introduced this idea of the shape function, what that represents for the elements, and so today we're going to extend that discussion to 3D elements. So we're going to talk about tetrahedrons, hexahedrons, both their linear and quadratic versions, and we're going to talk about their shape functions. Okay. I had originally planned to discuss the midterm project with you guys today, but I did not prepare it in time. So Thursday, I promise you, we will talk about the midterm project. Because at this point, we've done 3 ANSYS activities. At this point, you guys have a fairly good grasp of just the basics of ANSYS. And so, now is kind of the perfect time to introduce the midterm project. You guys to kind of start working on it. So. Timeline for the midterm project, I'm planning for it to be due kind of sometime end of March. So you're going to have about a month to work on it. Yeah, look forward to that on Thursday. So that'll be kind of the first thing that we discuss. We'll discuss maybe the first 20-30 minutes up Thursday. But just to kind of give you a heads up, the plan for the midterm project is for you to kind of do kind of like the ANSYS activities, but kind of just all on your own. So, for all the activities so far, I've kind of, held your hand a little bit in terms of telling you what mesh settings to apply, what boundary conditions to apply, what results to look at, how to present the results. For the midterm project, you guys are going to be doing a lot of that on your own. So I'm going to give you the geometry, and you're going to be running your own finite element analysis. So you'll be thinking about, what are the quantities I want to look for, what are the settings for the mesh that you want to apply, what are the boundary conditions you want to apply, and provide justifications for all of these things. Okay, so it's kind of like it's kind of what a very typical kind of finite element study would be like if you were to do one in industry. Okay, but I'm still preparing the geometries. I'm still preparing kind of the specifications. So we'll talk about that on. Okay. Any questions on anything before we get started for today? Yeah.
Okay, look, the midterm project do a little bit after.
When is the comp exam?
I think it's on the 20th.
29th of March.
And like the Friday is like the Friday.
Okay. I'll double check with Dr. Myrol when the comp exam is, and then I'll probably put the due date for the midterm project the week after. I don't want to push it too far back though, because then right after the midterm project, then we're gonna start on the final project. So, but if it's landing around the time of the comp exam, I'll push it a little bit. All right, any other questions on any of this? Okay, all right, so let's go ahead and get started. Okay, so plan for today is to talk about 3D elements. Okay. So just to kind of refresh your memory of what we talked about last Tuesday is, we talked about, we went a lot more in depth in terms of what the different element types are and what they kind of represent. Right? In particular, we focused a lot of our discussion around this idea of a shape function. Every element type has what's called a shape function, which basically it kind of describes the behavior of that element in terms of how they approximate the solution, how they approximate the geometries, how they interpolate the solution. So, the shape function is kind of the core feature of every. Right. So remember, we talked about, when you run the finite element method, when you apply it in practice, essentially what you're solving for is you're solving for a solution to a governing differential equation, oftentimes a partial differential. Right. And the way finite elements does this is that it first assumes a form of the solution and then solves for the best version of that function that solves that solution, right? Or solves that equation. And so the shape function determines what that form is. Okay. And so certain things to look out for is that, first of all, the number of terms or the number of unique terms in the shape function is determined by the number of nodes in the element itself. So one thing that we saw last Tuesday was that as our elements got more complex, as we went to like a quadrilateral, as we added mid nodes, then this increased the complexity of our shape function. Okay, and generally speaking, the more unique terms that you have, the better solution properties that you're going to have. So that's going to lead to better accuracy, in general. But in particular, you're going to be able to capture more unique types of solution behavior or more unique types of solution dependency than you would otherwise. Okay? So for example, one thing that we discussed, especially in our discussion, kind of comparing the triangular element to the quadrilateral element, was that the quadrilateral element had the presence of what we call a cross term or a pseudo-linear term. So if you recall, this was C3 x1. Okay. So this pseudo-linear term was not present in our linear triangle, but it was present in our linear quadrilateral. So the fact that we have this extra term there generally leads to better solution, just because we can capture more unique of behavior. Okay. I do want to dive in on this point a bit more, just because I think this kind of bears a bit more explanation. It's not an automatic that more terms equal better, and sometimes sometimes the difference is so marginal that you sometimes don't even notice it. Like if you go back to some of our previous activities, probably for those situations, if you change the element type from quadrilaterals or hexahedrons to triangles or tetrahedrons, you're probably not going to notice that much of a difference in the results. And there's a very good reason for that. Same thing for linear versus quadratic. So, for some situations, if you change from linear to quadratic, you're probably not going to see that much of a difference, even though the shape functions are, much better for quadratic. So I do want to dive into that. But the other thing I want to mention before that is that more terms usually also means more cost as well. Remember, when we mention cost, what I mean by that is computational cost. So the amount of time it takes to compute the solution, the amount of computational resources, the amount of memory, the amount of RAM. More terms generally means a higher cost to the solution. Right? Okay. So we're kind of going on this, on this tour of all the different elements, and we're looking at their shape functions just so that you kind of have a better idea in terms of what they all kind of represent and what you're actually trading off when you choose a tetrahedron versus a hexahedron. Okay, so this was just kind of a recap from last time, and this is kind of a good starting point for today. Are there any questions on any of this? Okay, so let's dive into this idea of what does it actually mean to have more unique terms, and why does it actually improve your solution? This is a little bit off script, by the way. This is not in the lecture notes. This is just kind of something I've kind of noticed over the years of this kind of being a little bit of a misconception. So I did kind of want to clear this up. Okay. So the point that I've kind of made over the years, and this class is no exception, is more terms in your shape function is generally better, or at least a more accurate solution. Okay. But what is better, right? A better finite element solution is ultimately one that matches reality as closely as possible. So if you were to take your finite element simulation and apply real life loads on the real life part, your finite element solution should match exactly what is happening in reality. Okay. there's no such thing as getting something that's more accurate than reality, right? And so, reality is kind of the upper threshold. So once you kind of match that, then you're kind of good to go. Okay. Okay. So what does it mean exactly to have more terms in your shape function, and what is that, how did that actually manifest in your solution behavior? Well, more terms in your shape function means that your finite element solution has more ability to capture different kinds of dependencies on the solution. So sometimes this is good. So sometimes the fact that, if you kind of pay the cost, you use a higher quality element, a quadratic element, a hexahedral element, then getting this extra kind of, this extra kind of, functionality, this extra dependency is good because your solution may actually depend on those variables. But sometimes it doesn't because your solution doesn't actually depend on those variables. Okay. All right, so there's a very simple example that we can kind of draw with this. It's very similar actually to activity 1. Okay. So let's say that we had kind of a very simple plate, right? So a two-dimensional object. And to this plate, we're going to subject it to a simple tensile force. We're just going to pull it apart, just like activity 1. The only difference is that I'm not going to put a hole in this plate. Just to kind of drive the point. Okay. So let's fix the plate. So we're going to fix the plate on the left-hand side. So it's going to have a displacement of 0 over on that side. And let's apply a tensile force on this plate. So we're going to take this plate, bolt it to the wall, and then just pull on it as hard as we can. We're going to try to kind of stretch it as much as possible. All right, so what do we expect is going to happen? So generally what we expect to happen is the plate is going to stretch out, right? So the whole entire plate is going to deform. It's going to be pulled to the right. But if you actually ran the simulation, what you're actually going to see is that the contour lines of the solution are all actually going to be vertical. So what does that mean? So that means, maybe this side of the plate is going to have max deformation. Maybe this side, this is going to be slightly less. This side is going to be slightly less than that. Should have kind of head because I've already kind of ran out of half my colors, but not halfway down the plate. But you can kind of imagine, right? But the point that I want to make is that you're going to have these kind of vertical streaks on your solution, where everything in kind of a vertical column there is going to have the same amount of deformation. You might see small differences, and so maybe near the edges, you may see some deviation from this kind of vertical pattern. But generally speaking, you should see kind of this vertical pattern throughout the entire plate, okay? And so if we draw a coordinate system on here, so if we say that we have an X direction going in the kind of traditional X direction horizontally, and we have a Y direction that's going vertically. One statement that we can say, after looking at the solution like this, that we can say that the deformation is only a function of X. And so the amount of deformation you see only really depends on how far away you are from the fixed support. But vertically, it doesn't really matter where you are, right? So if you're on the same X coordinate, you can go up and down the plate, and you're going to have experienced the same amount of deformation. And so what we can say mathematically is that our deformation is only a function of X. Okay, so it does not depend on Y. All right, so mathematically, what we can say is that the deformation, I'll call it D, is only a function of X. Okay. Okay. So why is this important? So why even bring this up? Well, we know that if we used shape functions here, our shape function is essentially going to try to replicate this this solution here as closely as possible. So if we call this d of x here, this is our true solution, right? Right. We know our true solution only depends on x. When we solve this in finite elements, our finite element solution is going to try to approximate this deformation field as closely as possible. Because that's what FEA tends to do. So FEA will try to take whatever, the true solution to your problem and try to approximate it as closely as possible. Okay. And how is it going to do this? It's going to use the shape functions of the elements in the mesh. Okay. So let's look at a couple shape functions. So let's look at the shape function for a linear triangle. So let's say if we took this plate and we meshed it with linear triangles, and let's compare that to the shape functions if we mesh this with linear quadrilaterals. Okay. Triangles versus linear. Okay, so the shape function for linear triangles from last time, we have C0 plus C1x plus C2 1. So we have three terms to our shape function for the linear triangle because we have three nodes in a triangle, three vertices, and so we have a constant term, a linear term in x, a linear term in y. For linear quadrilaterals, E of xy looks very similar, except we have the addition of that pseudo linear term, the cross term. Okay. So in this kind of very, very simple simulation here, in this kind of very, very simple case here. We kind of intuitively know and kind of intuitively understand that our solution is only a function of x. So the only term here that's actually going to be doing any work or anything that's going to be that's going to contribute to the solution is going to be C1x in both of these shape functions here. C1x, C1x. And so the way that we kind of described as that these terms are going to be the only ones that are active, okay? Because we know, because what do we know just intuitively just by looking at the problem? We know that the solution does not depend on y. And so if the solution doesn't depend on y, then it's likely when you solve for the finite element solution, C2 essentially is going to be equal to 0. That's what you should get, or it should be very close to 0. It shouldn't be, maybe not exactly 0. It's hard to get things exactly 0 computationally, but it should be much, much smaller than C1. And that's the same thing for C0 as well. So there's no constant offset in this case. And so, we do actually have a fixed support. So C0 in this case is also likely going to be 0. Because our solution it doesn't have any bias, right? And so it doesn't have any kind of offset. So C0 should also be 0. Okay. By that same token, our extra term, our C3 term, for our linear quadrilaterals is also likely going to be 0, because there's no part of our solution that actually depends on the combination of x times y. Since part And so even though C2 and C3 and C0, we'll throw that in there as well. And so even though all three of these constants are likely to be 0, the computer is still going to expend some effort to actually solve for their values. It's just going to go through all this effort only to determine that these are still 0. So it's going to do all that effort only to find out that those constants are just 0. Right? And so in this kind of very unique, kind of very contrived situation, you could actually make the argument here that linear triangles are actually more superior to linear quadrilaterals, which kind of goes against some of the logic that we may have discussed before. Because really, there's no point in computing these extra terms, because those extra terms there are not going to contribute anything significant to the solution. Right? And so if you go back to activity one, right, and so you open up your files for activity one. And actually, everyone did this too. So, and everyone did this in activity one where, you ran a simulation with quadrilateral elements. And I had you run the exact same simulation with triangular elements. And what most of you found in your activity reports was that there was no difference, right? And so for that very simple case where you have just a tensile force, the difference between quadrilaterals and triangles might be something that's very, very minuscule because the presence of the whole does make things a little bit nonlinear. But for the most part, it's going to be no difference. Okay. And so this would be a situation where, you're kind of just doing some extra work there for kind of really not any benefit. Okay. Now, granted, this situation here was pretty contrived. I kind of just made it up just now, but there are certainly situations like this in practice as well. It's just that, in practice, for a practical situation, you're probably gonna have more complex geometries, more complex loading. And so, you don't really know what the dependency is gonna be beforehand. But sometimes it could just end up just being some extra work. And, for the simulations that we're doing in this class, probably it's not that big a deal. It's probably the difference between waiting 2 seconds for a solution rather than 3 seconds, which is, not really enough time to do anything, except maybe, pick your nose. But, but for higher level cases, for bigger meshes, bigger simulations, this does make a difference. And this actually does make something that it is something that you should consider when you're running these finite element simulations. Okay. Any questions on this? One other thing that you can say is that, because we're using a linearly elastic material, that's kind of the material properties that we have here, is that one thing you can also say is that this deformation should progress linearly from the left to the right of this plate. Okay. And so what we can say is that this d of x should have a linear tendance x. Okay. And that's strictly just because of the chosen material properties for these for this problem. Okay. And so if our solution is going to be linear on x, then in this case, we actually don't really get any benefit from using quadratic elements either. Okay. So there's actually kind of a really interesting kind of interplay between your choice of material properties and your choice of material model and the element type that you choose as well. Okay. Now, this does not mean that you should just go with linear all the time, right? So there's more complex interactions with the geometries, in terms of getting nonlinear deformations. And so, this does not mean you should use linear elements, because remember, shear mocking is still a thing. And so, shear mocking is something that you want to be worried about. So, I would say that for everything in this class, it's still safer to use quadratic, but there are situations where going quadratic, doesn't really give you any really tangible benefits in terms of solution accuracy. Okay. So I wanted to give some more context on this just because, I think in the past, I've kind of given the approach of, just use quadratic for everything, which, for this class works well, but, there are situations out there where you might actually want to go for a linear element, because, you don't really get that much benefit for going quadratic. And so I want you guys to kind of think about this a little bit, especially as the midterm project is going to start to come around. And so, maybe some of your midterm projects, I haven't chosen the geometries yet, but, it might actually be okay to use linear elements for these. One thing to kind of think about. Okay, So let's go, so now that we've kind of, given a bit more context to what the shape function represents and what it's actually used for, let's actually get into the 3D elements. Okay, so we're gonna kind of have the same kind of trajectory that we did last Tuesday. So let's start with the simplest 3D element, which is the linear tetrahedron. Okay. So the tetrahedron is a shape that everyone should be familiar with. It's been part of our activities 2 and 3. But let's actually draw it out and see what its shape function actually looks like. Okay. So the name tetrahedron, tetra means 4. So a linear tetrahedron is a 4-sided polygon. Okay. Something like this. So every facet of this tetrahedron is a triangle, which is kind of 4 triangles kind of merged together into one 3-dimensional shape. Okay. So not only are there 4 sides to this shape here, there are also 4 vertices. I'm going to go ahead and label them 1, 2, 3, 4. Again, it doesn't matter exactly the order in which you number them. I'm just doing them just to count. Okay. And so since our element here has 4 vertices, that means the shape function is also going to have 4 unique terms. T of x, y, and z. Okay, remember we're in 3 dimensions, so we have to include the z coordinate as well. So our 4 terms here are very straightforward. These are all just the first order linear terms as well as the constant terms. We have C0 plus C1x plus C2y plus C3z. So now that we're in 3 dimensions, we have to account for the z direction as this. So this is kind of the simplest kind of shape function or the simplest kind of element type that you can use in 3 dimensions. And we really just kind of have the bare bones of shape function. All right, so all the pros and cons of a linear tetrahedron are very, very similar to the pros and cons of a linear triangle. Okay. So kind of the biggest benefit or the biggest pro that you have for a tetrahedron in general, so this is both linear and quadratic, is the fact that they have what's called the simplex property. What that basically means is that you can basically fill almost any volume with tetrahedrons and it should fill fill well kind of without fail. So essentially what that means is that when you try to mesh a geometry with tetrahedrons, it's very rarely going to fit. So, there might be some situations where maybe the mesh size that you chose is too large. Even with the tetrahedron, then your mesh is still gonna fail in those cases. But if you pick an adequate size, if your geometry isn't too, insanely crazy, and you pick a tetrahedral mesh, you should get a mesh out of it without any fill, which is really valuable. Right. So of course, the downside here is that, our shape function here is purely linear. And so that means that our solution, our finite element solution, can only capture purely linear variations in our primary solution there. So just like we discussed kind of earlier today, so if your primary solution variable has just a pure linear dependence, so you have a very simple case where maybe you just have a load in one direction and your variation is only in that direction, then you can capture it. Anything more complex than that, then a linear tetrahedron is going to struggle to capture. Okay, it's sometimes it's not going to do too bad a job, and so sometimes if your mesh is fine enough, even a linear tetrahedral element will still be sufficient. But oftentimes this kind of places a lot of burden on the amount of elements that you need. That's usually the case in kind of the general situation. And oftentimes, just the perception that people have in linear tetrahedrons is that if you present a study where you are using linear tetrahedrons, then the expectation for people to kind of, read your report and to kind of have faith that you do have a reliable result is for there to be enough mesh density. Okay, so it's oftentimes you need a lot of mesh elements. But again, linear tetrahedrons, they can get the job done. So there's nothing wrong with them as long as you're aware of their limitations. Actually, for my entire graduate studies, and I did kind of computational fluid dynamics simulations of blood flow, linear tests are the only one or the only elements I used, just because I kind of had limitations in other areas as well. I was able to make it work, but so you can make it work, just you have to kind of be aware of its limitation. One of those limitations is the fact that any derivative-based quantity is going to have very, very low accuracy with linear tests. So any solution that depends on the derivative of the primary variable, so things like strains and stresses, those are going to have even lower accuracy. Okay. The reason is that if you take the derivative of our linear shape function, you end up with a constant value. That means for any derived quantity like stress or strain, if you want to get any variation, it's going to be element to element. So, but for within each element, the stress is going to be constant within that element itself. And if your element isn't small enough, then you end up with kind of a not a very good situation. Okay. So this fact, if you remember, this fact is what leads to a phenomenon known as shear loss. If you have linear elements and the elements are not adequately small, the elements are gonna kind of lock up because you don't have a variation in stress that's needed to produce these deformations, okay? So shear locking, generally a very bad thing, you don't want this, not good. Okay. So if you're just starting out, if you're just kind of learning ANSYS for the first time, I would say just avoid using linear elements. Because you don't want to get into this, you don't want to even put the risk of shear locking to occur. Because sometimes it can be hard to determine if it's going to be hard. Sometimes it's hard to look at your results and say, you know, whether shear locking occurs or not. And so, for you guys, you guys are kind of just learning ANSYS for the first time. I would say just use quadratic elements. It's much less of a risk there. You're going to incur some additional cost, maybe, but a lot of times maybe it's good just to give you something. Okay, but that's linear text, and so linear text is kind of the simplest you can do, but there's still a lot of really great things you can do with linear text, as long as you're aware of its limitation. All right, any questions on this? Okay, all right, so let's go ahead and move on to the next element. Let's go quadratic first. Let's look at the quadratic tetrahedron. Okay, so the quadratic tetrahedron is going to be just the quadratic version of the element that we just drew. Okay, and if you recall from last Tuesday, the primary way that we take an element from linear to quadratic is we add mid nodes. So for every edge that's in the element, we add an additional node there. Okay. Here. Okay, so we have all our vertex nodes, 1, 2, 3, 4, and then we're going to add a node to every edge in this element here. You're going to add a node here, 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 and then one in the back as well. So there should be 10 overall. 5, 6, 7, 8, 9, 10. Perfect. Okay, so that means our element now is going to have 10 nodes. That means our shape function is going to have 10 terms. Okay, so let's go ahead and draw this. So our shape function here, t of x, y, and z, c0 plus c1x plus c2y plus c3z. So those are all the linear terms that we had from our linear tetrahedron. Now let's add the quadratic terms. We have c4 x squared plus c5 y squared plus c6 squared. Okay. So those are all the straight up quadratic terms. So it's just the same variable multiplied again. Then we have the hybrid terms. We have plus c7 xy plus c8 yz plus c9 x. All right, so it's a lot of terms. Wait till you see the quadratic hexahedron. That one. Okay. And so, like we kind of talked about at the beginning of class today, more terms here means that, these elements have a lot more capabilities. To approximate different solution behaviors. Okay, so basically any quadratic dependence, any dependence on kind of two variables at the same time, then this element can capture that. Right, kind of the main benefit that you get for the addition of the quadratic terms is the fact that any quantity that has kind of a very fast change, you can capture that better with a quadratic. Because the main difference between linear and quadratic, polynomial, not even just looking at finite elements, is that a quadratic function grows a lot more quickly than a linear function. So anytime you have a solution quantity that's going to change very rapidly in a very short period of space, a quadratic element is going to perform much better in those situations. But yes.
For their applications, do they have to? Can you go back here?
Sure.
Would you have to maintain it this kind of perfect shape with it, like, for example, side 1 for be longer than side 4 to be, I guess, stretch?
Oh, yeah, absolutely. Yeah. So what I drew, so the question is, are these tetrahedrons, quadratic tetrahedrons, are they required to kind of maintain this perfect shape? And definitely not. So there are going to be situations, especially if you're meshing kind of a more complex geometry, where these tetrahedrons have to be kind of skewed and kind of squished. Maybe one side is much longer than the other one. So that happens actually very commonly. And so one thing I actually forgot, so someone mentioned it actually right before we left on last Thursday, is that you can actually check the quality of your mesh. And so you can actually ask ANSYS to say, how many of my elements here are actually kind of this kind of good, nice, equilateral shape, and how many are actually very skewed. Because that ratio of how many skewed elements you have can also be a predictor of mesh quality. So yeah, so remind me, let's remind me to kind of show everyone how to do that on activity 4, because it is a very useful thing, and actually one thing you can use for your project as well. Yeah, absolutely not. So these elements can be squished and stretched and stuff.
You mentioned that the speed elements give you speed to elements lead to less accurate result.
It depends sometimes, and so generally the expectation is that if you do have a lot of skewed elements, then that's not good for your solution. Because a lot of times, when you're computing derivative-based quantities and you have two nodes that are really close and one node that's really far, that's usually not good. But there are ways to mitigate that as well, which I think ANSYS does. Although ANSYS is proprietary with a lot of their algorithms, So there are ways to mitigate it, and so generally we want to avoid that, but generally you want to avoid having to smooth it. And so you can do that by, a lot of times it's kind of smoothing your starting geometry, so taking your CAD file. A lot of times, because those skewed elements appear at sharp corners, and so just doing something simple like adding fillets to your geometry, or making it so that you don't have two parts that are kind of awkward attached together. We'll talk about that a lot more kind of as we get to more advanced meshing. But sometimes also it's just making the elements smaller will help to not skew the elements. Okay. Yeah, so for situations where you have kind of a rapid solution change, quadratic elements are going to help with that. Okay. And kind of as you gain more intuition, you gain more experience with finite elements, you start to gain, you start to kind of know, like, all right, this area in my mesh is going to be a problem area because I'm applying this really big force right next to a fixed constraint. And so I'm going to have a very rapid change in solution here. So, maybe I should, beef up the elements. And so that's kind of something that you kind of, start to get intuition for. So, if you notice in the last couple of activities, there's one part of the activity where I asked you to make predictions, which, we kind of skip it in the lecture just because I kind of forget about it. But, I do that on purpose so that, when you run these simulations, you should have some expectation. You should have some kind of prediction in terms of what you expect the results are going to look like. And that's going to inform you in terms of, where should you put the elements? How should you arrange the mesh density? So that's a very important step that I kind of skip in the lecture just because, I kind of, so kind of make sure that you're really thinking about that, especially for your midterm project. But of course, just like we talked about at the beginning of the class today, sometimes these extra terms can also be useless. If you don't have rapid changes, or if you don't have kind of complex dependency, then you may just do all of this computation just for numbers. And in 3D, it actually makes a pretty big difference, because if you look at the number of terms in the shape function for the quadratic tet compared to the linear tet, there's actually 2.5 more terms here in the quadratic tetrahedron than the linear tetrahedron. So that's pretty significant. And so, if you think about it in terms of, it's going to take 2.5 times more memory, 2.5 times more computing time to get the solution, that's not trivial. And so again, for the simulation that we're doing, it's going to be hard to really notice it. Because, when you hit solve, it's not, the ANSYS doesn't spend that entire time just solving the linear system. There's a lot of time that it takes to actually prepare the memory and stuff like that, prepare the all the matrices, and that amount of time is fairly consistent, no matter how complex your mesh is. And so it's a little bit hard to kind of see this 2.5x cost for the simulations that we're doing, but for the higher the higher element count simulations, this absolutely makes a big difference. And so this is something really careful that you want to do. So going quadratic, brings a lot of benefits, especially for, rapid solution change or derivative-based quantities. Stresses and strains are going to be much more accurately, estimated using quadratic elements, but, it is a conscious choice that you do. All right, any questions on the quadratic tetrahedron? So the quadratic tetrahedron also still has the simplex property, so that you still get the benefit from that. So a lot of people think the quadratic tet it's a very reliable element. So you should be able to get a good mesh out of it. It's going to have good solution properties. It's just sometimes it could be a big cost increase over time. Okay, so let's move on to the hexahedrons. So we are running a little bit out of time. So some of this may bleed over into Thursday, but that's Let's look at the linear. Okay. So the hexahedron is kind of another fancy way to just say it's a box, and so it's a six-sided Amazon package of an element. All right, so we have 6 sides to this box. Number of nodes that we have is 8. Thing with 3D elements is that you do have to draw the node in the back, and sometimes it can be hard to draw. So let's count these, make sure I can do the box correctly. Right, so we have all 8 nodes here, and so that means our shape function here is going to have 8 terms associated with it. Okay. P of x, y, z. All right, so we're gonna have a lot of pseudo linear terms here because there's only 4 linear terms. So we have to kind of borrow from the pseudo linear. All right, so we have C0 plus C1x plus C2y plus C3z. Okay. So those are all the pure linear terms, and so and the constant term. But we need to add 4 more terms here. So let's add all the cross terms. C4 xy plus C5 y plus C6 xz. So those are all the pseudo linear terms in 2 variables. So xy, yz, and xz. But we're still 1 term short, and so we need to get 8 terms here for a full solution. And so we need to actually go into the cubic terms here, which is x, y, z. So technically it's pseudo linear because each of the individual variables are linear, but in actuality it's a cubic term. Plus 7 x, y, z. Okay. So pros and cons for the linear hexahedron. So the most obvious con is the shape, and so it's sometimes a lot more difficult to mesh a geometry with hexahedrons. A lot of times it's actually impossible to get a full mesh of all hexahedrons. That's why the setting within ANSYS itself is called hex dominant, because oftentimes ANSYS is going to try to fill the mesh as much as it can with hexahedrons, but there's always going to be some weird nooks and crannies and corners and areas where it has to put a 10 in there as well. Okay, so it's very difficult to get a full mesh with hexahedrons, and sometimes even just attempting to mesh with hexahedrons will just lead to an error. Meshing error can often be the most frustrating part of working with FEA. Because oftentimes the error messages are not helpful. ANSYS will just tell you that the meshing failed, and then you're going to ask why. And then, ANSYS is gonna say, suck one, because it doesn't want to tell you what went wrong. So yeah, meshing error is very frustrating, although ANSYS is on the spectrum of meshing software, ANSYS is actually on the better end. There are definitely research softwares out there that are even more difficult to work with the meshing error, so. But that's kind of the downside that you draw with hexahedrons, that you're gonna spend, but you're probably gonna spend more time in the meshing. Just because you're gonna try to get around the errors, you're gonna try to modify the sizes in order to get the mesh to work out. But if you can get it to work out, there are benefits to it. And so the main benefit, the most obvious benefit, is in the shape function. So the shape function for the linear hexahedron has a lot more capabilities, has a lot more terms than a linear tetrahedron. In fact, it has twice as many terms, and so there are 2 times as many terms. So all of the cross terms, all of the pseudo-linear terms, those are all very beneficial, right? And so just like we said before, this can lead to better solution quality, better solution accuracy. Particularly in cases where you have complex loading, where you have kind of complex dependencies on your solution. So there's a lot of kind of cross dependency on 2 variables at the same time. So the linear hex is gonna flourish in those cases. And in particular, one big benefit that the linear hexahedral has is that when you take derivatives of the shape function, you don't necessarily get a constant term. So you still have some variable dependence on your derivatives because of the presence of those pseudo-linear terms. All right, so these are all kind of the same benefits that the linear quadrilateral. It's just now that we're at the lead. Okay, any questions on this? Okay, so last thing that we'll discuss today before we head out is the quadratic hexahedron. So kind of the Rolls Royce of finite elements, at least in ANSYS. Okay, so the way that we're going to derive the quadratic hexahedron is the same as we've derived all quadratic elements, and so we're going to add a mid node to every edge of the hexahedron. And the hexahedron has a lot of edges, and so I'm probably gonna miss 1 or 2. So hopefully it all adds up to 20. It should add up to 20. But we'll see if my geometry and my hunger. Okay, so there's our hexahedron. Let's go ahead and start counting the nodes. Let's start with the vertices. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Let's start. We got all the vertices. We got all the mid nodes. Well. By the way, I'm just kind of numbering these haphazardly, but you know, there's a better logic to numbering these than what I did. But there's 20 of them. There's 20 nodes to the quadratic hexahedron. So that's kind of the main. So if we have 20 nodes, that means our shape function here is also going to have 20 terms. And so, you know, we have about 5 minutes left, and so it's going to take me all 5 minutes just to write down all these terms here. Okay. Let's start. Something it out. Okay, so of course, you know, with 20 terms here, you know, this is not something that you will do lightly. Even though, you know, I've told you guys that this is kind of the what you would normally strive for with your mesh. But you know, per element, you know, the cost is actually pretty high for a quadratic hexahedron. Okay, so shape function T x, y, z. So first we have the linear term C0 plus C1x plus C2y plus C3z. Okay. Then we have the straight quadratic term, so C4x squared, C5y squared, plus C6 squared, plus C7 y, C8 yb, C9 xz. Okay, so those are all the pseudo-linear terms of the first order. Okay. How many do we have now? We have 10. Halfway there. Okay. All right. Next, we have what I call the pseudo-quadratic terms. So these are going to be terms that have one variable that's quadratic, but it's going to be multiplied by another variable in the system. Okay, so plus C10 x squared y. And so you can see here that this term is quadratic in x, and we multiply it by y. So technically this is a cubic term, but you know it's pseudo quadratic because we only have up to x squared. C11 x squared z. And we have all the same terms for y and z as well. So we have plus C12 y squared x plus C13 squared z plus C14 z squared x plus C15 z squared y. Okay. So that's 16 terms, and that's all the doublet terms. So those are all the terms that have just two variables in them. But we're not there yet. So we need to get up to 20 terms. We have 20 nodes in our element. And so now we're adding the triplets. Okay. So the first triplet that we have is C16 x, y, z. Okay. So that's the pseudo-linear triplet term that involves all three variables. Then we have the pseudo-quadratic triplet terms. So we have C17 x squared yz, C18 x y squared z, C19 x y squared. Whenever you have an equation that takes up 2/3 of the screen, you know it's something that's serious. Okay. So you can see here that, every polynomial dependence under the sun is within this function itself here, so, if you have a finite element solution and it depends on X, Y, and Z, this function is gonna cover its dependency somehow. Unless it's a cubic dependency, which is quite rare, actually, so. That's why, generally speaking, if you can get a quadratic hexahedron mesh, then, you're good on any solution accuracy problems. That you have there, and you could probably get away with a fairly coarse mesh as well. Okay. And all the benefits of a quadratic hexahedron are kind of the same as before, so I'm not going to repeat. So a better kind of solution dependency here, better solution quality at the cost of, well, computing all this extra. Okay. So when we come back on Thursday, we've spent kind of the majority of the time last Tuesday and today talking about element order. But we've kind of neglected to talk about element shape or element size, excuse me. And a lot of times, element size is a greater actually predictor of element of solution accuracy. But it turns out element size, element shape, element order, they all kind of work together to kind of build the quality of your mesh. Okay. So when we come back on Thursday, we're going to start with the topic. I'm going to write it down so I don't forget. Which is kind of the definitive test to see whether your mesh is a good quality or not, which is called a mesh convergence test. And when we talk about the mesh convergence test, then kind of all of this discussion on the elements, kind of hopefully it'll all kind of piece everything together. So element shape, element order, element size, the mesh convergence test will kind of, summarize all of that kind of forward. All right, but with that, we're out of time for today. So thank you guys for coming today. Hope you guys have a good rest of your evening, and I will see you all on Thursday.
The bottom one is not, but then I. So, no. This like. This one's not right.
Yeah.
One more module.
Yes.
Hey guys, thank you. Our question, are we gonna be using computers for convergence tests? Well, if for the project you want, so for the project, you do need to use the computers for the convergence tests. But on Thursday, we're just gonna talk about the concept of the convergence test. So no computers needed for Thursday. Thursday is just a straight up that.
Yeah,